Hello everyone. So welcome to the mind map of gravitation, which is the next part of our mind map series. And in this chapter, we will be mostly concerned about the laws of gravitation, accelerations, and Kepler's laws. And this is the application part, which is the most important part from your exam perspective. So let's quickly get into it. First of all, Newton gave a very universal law of gravitation. It is applicable to any two masses in the universe, which is when there are two bodies separated by a distance r having a mass m1 and m2, then the force exerted between them due to the gravitational force is equal to some constant, or we can talk it in terms of proportionality. It is proportional to mass m1. It is also proportional to mass m2, while it is proportional to the inverse of r square, or it is inversely proportional to r square. This was the basic proportionality given by Newton in the field of gravitation. And when you combine all of them, you convert proportionality into equality. What we get is F is equal to m1 m2 by r square and some constant associated with it. This k is actually called the universal gravitational constant gravitational constant, and it has a value of 6.67 into 10 to the power minus 11, and the unit is Newton meter square per kg square, because it is relating something in the order of Newton, these two multiplied as kg square and this multiplied as meter square. So when you find the unit of k, you can put it here and divide the whole thing by m square. Anyway, so this was the Newton's law of gravitation, based on which we are going to see very interesting applications. But before that, uh, you can quickly glance through these very basic things, which is that it is a very weak force in nature. Why is it weak? It is weak relatively as compared to Coulomb's force, maybe between the charges. It is very high actually, because if you have 1 coulomb and maybe 1 meter is the distance between them, then the force exerted between them is something order of I think 10 to the power 12 newtons. And in the same manner, if you have two bodies of 1 kg each and separated by a distance of 1 meter, then the attractive forces between them is going to be just around 6.67 into 10 to the power minus 11 newton. Do you understand the difference of scale between both of these? This is why gravity is called as one of the very weakest forces in the nature. It is central as well as conservative. Central because, for example, there is this body, and maybe there is this another point mass. Then the gravitation can be associated with the manner of the center of mass of this body and the second mass. So you can always direct the acceleration towards this direction, towards the center of this body, center of mass to be precise. That is why it is central in nature. And and why is it conservative? First of all, what is a conservative force? Conservative force is that force in which, no matter, let's say you are going from A to B using some force which is conservative, then no matter what path you take, the work done will be the same. And if you can do a closed circle or closed loop in whatever shape you close the loop, and you come back to the same point, then the work done will be equal to zero. These are the things for a conservative force, and that is why it is a conservative force. Because see, I'll give you one example for this. That let's say there is this body of m mass, and you have to push it through a height of h. Now you can even do it, push it at the height h, or maybe you can do something like this, or maybe you can do something like this. These are the several paths which are possible, but in each of the case, the horizontal part of the journey of the particle does not account for any work. That's why only vertical part, which is this part and this part, which will add up to the whole length. That's why whichever path that you take from going from a point to b point, the amount of work that will be done will be exactly the same. That is what is the meaning of conservative force. Always attractive in nature, that's the basic fundamental property of the force. That whenever there are two bodies having some mass, then the force between them is always attractive, it is never repulsive. Actually, it is different from the Coulomb's force on the charges, in which it can be repulsive as well as attractive. But this gravitation is always attractive in nature, applicable to all bodies irrespective of the shape, size, and position. Of course, because let's say there is this body of this shape, it is made up of particles, right? It is made up of particles. There's this one another point mass. Then if it is made up of particles, then each of them will attract the this mass, right? And it will accumulate, it will add up to a point which will be the center of mass, and you can directly assume this body to be a point mass center at the or situated at the center of mass, and then you can apply the equation of Newton for the gravitation. So these were the basic fundamental properties of the gravitational force. What we are going to discuss now is probably acceleration, because that's the most basic thing which will result from any force per se, right? Let's say there is this force which is in, let's say, 10 Newton. If the body is of 1 kg, and if a force of 10 Newton is being applied, of course the acceleration will be 10 meter per second square. 10 meter per second square, because force always results into acceleration, because force is equal to m into a is a fundamental equation of motion, Newton's equation of motion, laws of motion, where mass cannot change. So if force is increasing, acceleration will also increase. In the same manner, if you have a gravitational force which is something of g into m1 m2 divided by r square, then it must also be equal to, let's say we are calling this m1 and m1 and this one m2. We are actually calculating the acceleration of m2 body, then it must be equal to m2 into some acceleration, right? If we are only looking at the body 2, what is happening to the body 2, then we must be concerned about its acceleration, because some force is acting on it. It means if you take both of them, m2 gets cancelled out, and which means acceleration is equal to gm1 by r square. So what it means is, if m1 is massive enough, then acceleration of the body m2 is not dependent on the mass m2, but it is only dependent on the mass m1. All right. So this is the acceleration which will be the result of gravitational force. Let's take the example of Earth. This is the Earth, and this is the radius r. Of course, on the surface, if a person is there, its mass and dimensions are uh, uncomparable to the mass and dimensions of Earth, right? So what will happen is, if let's say this person goes to a very small height and jumps back, with what acceleration will it get attracted? We can simply find out. Let's say this is the mass m of the body and capital mass M of the Earth, and this is the radius of Earth, re. Then we can quickly calculate the force. Force will be equal to, or the gravitational force, what I told you was, when there is a large body, you can assume that large body, the whole mass to be concentrated at the center of mass of the body. And of course, for a sphere, the center of mass is going to be the center of the center of the sphere. G into mass of the earth into small m, divided by what is the distance. Since I told you it is very small height, I can safely assume it to be the equal to radius of earth, right? So radius of earth whole square, and this must be equal to the force that is being experienced by this small body or this small person, and that will result into the mass of the person into some acceleration, right? I can call it maybe g, ag, acceleration due to gravitational force of the earth. That will be equal to m into acceleration due to gravity, and here m gets cancelled out. What you're left with is acceleration due to gravity is equal to g capital Me, where Me is the mass of the earth and Re is the radius of the earth. This thing gives you what we know from the first chapter is acceleration due to gravity. This is what is what results into the acceleration due to gravity. Okay, I hope this is clear. I think this part has been clear as well as this part. Now there is certain degree of variation on different places on the earth, depending on maybe height, the situation, or the if you remember from geography, something called latitude. We will discuss all of that. First of all, let's say there is this earth, and of course on the surface of the earth, the acceleration due to gravity simply comes out to be, when you calculate all of this, it comes out to be 9.81 meter per second square. All right, no problem in this. Now uh, and one more fact is there, that see, this 9.81 is kind of average, because it actually varies from the pole to the equator. Actually, we will come to that, and after that I'll tell you the aberration that is there. It is not constant. So first of all, let's come to, let's say there is this another point which is at a height h from the surface. This is the radius Re. Then of course you can write the acceleration due to gravity on this point A at h is equal to gme divided by the whole length squared, right? This whole length squared, that will be Re plus h, the whole square. Now in mathematics, you must have gone through something called binomial expansion. I'm not going to get into that, but when you do a binomial expansion, you'll get something like gme Re square 1 minus 2h divided by R, and some other terms which has a variable or which has a multiplier of h square or h cube, things like that. But since I have already assumed that h is very small as compared to Re square and Re cube, then this whole thing, if you square, already h by Re is a very small number. If you make a square of it, for example, it is 0.01. If you make a square of it, it becomes 0.001, which is very small. So of course you can ignore them with respect to this term. All right. So that's why we only take this term for small height, and that's how you get acceleration due to gravity at a particular height which is less as compared to the radius of earth. It is nothing but, what is this term? This term is nothing but acceleration due to gravity. I can write g into 1 minus 2h by r. All right. So this is the acceleration due to gravity at a particular small height with respect to the radius of earth. Now Coming to let's say there is this earth, and if you have dug a tunnel to a particular depth d, and on this point you want to find out the acceleration due to gravity, in this thing what you have to do is, actually, acceleration due to gravity is because of the mass associated with this thing, the whole mass of the concentric sphere, which is inside inside this point, not outside. All right. And if you calculate closely this one, shall we do that? I think we can. G m m dash divided by re dash squared, right? That should be the acceleration due to gravity. But m dash, how can we calculate m dash? This is the re, the whole thing, and this can be said as re minus d. All right, no problem. So this becomes, and how can you find mass of this thing? Mass is, how can you calculate the mass? It will be the actual mass of earth into uh, the radius, which is re minus d, divided by re the whole cube, right? So we can write it as me into re minus d whole cube divided by re whole cube, divided by, what is re here? Re dash, it is nothing but re minus d the whole square. Now this term and this term is the same, so what I'm left with here is, sorry, just a second, it is equal to gme into, what is that, re divided by re cube minus d divided by re cube. If you calculate closely, this becomes gm by re, I think one of them will get cancelled out and this will become square, re square, and this is 1 minus d by re, radius of earth, right? And what was this term all about? Since we have taken the original mass of earth and original radius of earth, this comes out to be nothing but acceleration due to gravity on the surface multiplied by 1 minus d by re. This is the acceleration due to gravity at a depth h, not at a height, at a depth. I hope this is clear. Where were we? Yes, we got the same results, and we are going to discuss this one. It's very simple actually. Some people overly complicate it, but it's not so complicated. What it talks about it is, of course, you have acceleration due to gravity or force due to gravity, but we also have something called a rotation of the earth around its own axis with some omega, right? Of course, that's why we have days and nights. So let's say this is the center of the earth, and you are at a particular angle. Let's say this is the, and you are at a particular angle theta. What you basically will experience is some centrifugal force because of the rotation of the earth, and that will be equal to omega square into r dash, which where r dash is this much length, r dash, right? This will be the acceleration, and there will be another acceleration due to gravity, which is nothing but g, right? Now what I have here is, this person will actually experience, see, the gravitational force is acting on downwards. The acceleration due to gravity is always experienced towards the center of the earth, right? So what you have to do is take the component of this horizontal force in this direction, so that you can subtract it from this part. Now if this angle is theta, you can definitely write it as omega square r dash into cos theta. This is the acceleration in this direction, and this is g. So I can definitely write it as in the format of g dash at a particular angle theta is nothing but omega square r dash into cos theta. But this r dash doesn't look good. We can convert it in the form of re, which is the radius of earth. In this triangle, if you look closely, if this is the angle theta, this should also be the same angle theta. Even you can look into the alternate interior angle, the same angle theta. In this triangle, can I say re into cos theta is actually equal to r dash? This is the re and this is the r dash. This is the angle theta between them. So I can replace r dash with re cos theta. I'll do that. G dash at a particular angle theta will be equal to omega square r into r dash. What is r dash? Re into cos theta into cos theta. This was this particular component, but there is another component which is acting in this direction, so I'll just subtract it from this one is equal to this thing. So I can conclude that it is g minus omega square r cos square theta. Not so complicated. So this was this thing. Of course, when I put 90-degree, the cos theta component becomes 0. So this will be g is equal to g. But when you put angle is 0, it means you're at the equator. You're at the equator, that's where the angle will be 0. You will get the minimum amount of gravitational force, which will be equal to g is equal to g minus omega square r. So what we got from here is, on the equator you have the least amount of gravitational force acting on you, while when you are at the um, pole you have maximum amount of gravitational force, which is the original gravitational force, not due to a pseudo force which is acting on you. There's another reason why the force on the, or the, let's say this is the earth. When you spin a body which is somewhat flexible, of course the earth is slightly flexible, it is it is a solid body, but let's take the example of a clay. If you rotate it, of course it will try to expand on the horizontal part, and that's what happened with the earth. While it rotated for billions of years, the shape of the earth is not a perfect sphere. It is not a perfect sphere, it is actually spheroid. What is a spheroid? It is a shape which almost resembles a sphere. It is not a perfect sphere. What happened was, due to the rotation, continuous rotation, the earth actually looks something like this. Of course I'm making the changes very much visible, which it is not in the real parameters, but this radius r dash is actually equal to this radius. Oh sorry, it is slightly greater than the distance from the center of the earth to the pole. All right, so that's another reason why we have gravitational force higher um, on the pole, because from the center of the earth the distance is smaller, and if you calculate the gravitational force, F is equal to gm by re square. If you decrease this one while keeping the mass constant, the whole force will increase, right? So that is that's why there are two reasons for poles having slightly higher gravitation than the equator, because of one, the rotation of the earth first of all, which leads to centrifugal force, which can also be called as this centrifugal force, and what was that another one, which is elongation of the earth along the equator and shortening along the pole. So these are the reasons why these three variations happen, and we can come back. Let's take the example of a satellite, shall we? Yeah, we can. I think we can discuss that. No problem. Satellite, right? For example, let's say this is the surface of Earth, or this is the Earth, and you have a satellite. What are satellites? Satellites are the bodies which continuously rotate around the Earth at a fixed orbit, at a fixed orbit, at a constant continuous speed, or at a uniform speed. Let's say it has a speed of u. All right. Now, and it is having some height h, or maybe we can take it from the center, the r, small radius r. Now, how can we find at what speed it is rotating at a radius r, or orbit of radius r around the Earth? We can do that because there are two forces which will be acting on it. First, centrifugal force, and another one will be gravitational force. Only when these two are equal, only in that situation it will continue in a fixed orbit. Otherwise, the length or the radius of the orbit will increase or decrease depending on which one is bigger. Because in a uniform circular motion, there is no tangential acceleration, right? There is only radial acceleration, which is actually equal to the centrifugal acceleration. Now, when we calculate the free body diagram of this body, it comes out to be, let's say it has a mass m, and the mass of Earth is capital M. Then you have gm small m divided by smaller square is equal to what force it is sorry, what is the force it is experiencing due to the centrifugal force? It should be equal to m v square or u square divided by r. As simple as that. One of the r goes away and the m also gets cancelled out. What you're left with is u square is equal to gm by r. So u is equal to under root gm by r. This is the speed at which any satellite should rotate around the Earth. All right. Okay. So this was the satellite, and we can also take up one example that let's say you have something called International Space Station, right? In which there are astronauts going and staying there for scientific experiments and all. Let's say there's this person inside the International Space Station. What will be the gravitational force or effective gravitational force acting on it? Of course, the gravitational force will be in this direction, but the same amount of force will be acting on the other direction due to the rotation, centrifugal force, which will result into F net on the body is equal to 0, which means it is freely floating inside the International Space Station, freely floating. No effective gravitation. No effective gravitation. All right. So these are the effects of staying on a satellite. Now, if that is clear, let's take up orbital speed. We can even, this has been given in this format. We can take up in this format. Let's write it as, let me just take it, what we need to discuss here. The escape velocity, orbital speed. Orbital speed, I already explained it to you how to find it. Actually, in this type of problem, you always have to make a diagram like this. and the best way is to calculate the forces. That's how you don't have to, even if you don't remember in the exam, you will be able to figure it out. Let's take an example of escape velocity. But before knowing escape velocity, I have to introduce something called potential. What do we call, or what do we understand by potential? Gravitational potential. Gravitational potential. Because it must also be there in the mind map that you have, I guess. Yes, this is the part of gravitational potential. Or maybe because before gravitational potential, I can take up gravitational intensity. It will be easier for you to understand potential if you have the idea of intensity. First of all, there is this force due to Newton's law of gravitation, which is Gm small m divided by r square. Now, um, can we imagine this force to be something like, let's say there's this creature called a spider. How does it catches the prey? It catches the prey using a web. It creates a web around it, and whenever a fly is uh, going inside the web, it gets stuck to the web, due to which the spider knows that there is a prey, and it comes and eats it. But why I'm telling this is because gravitation also acts in the same very basic same way, because any body or any mass m, actually around it there is some sort of web of forces, or some sort of web in which, if there is another particle of any mass m comes in the contact of that web, it will experience a force which will be exactly equal to this thing. All right. And this web that I'm talking about, analogy that I'm making, is actually equal to the intensity, gravitational intensity. We define it, intensity is equal to G capital M divided by R square. It is very much almost the same formula as this one. It's just that this did not appear in this equation because, of course, the spider's web is independent of the prey, right? When it was created, it didn't know that which prey it is going to catch. So, of course, it is independent of the small mass m. But when a small mass m interacts with the gravitational field, field intensity, yes, gravitational field, then the force that is experienced is equal to the gravitational field multiplied by the small mass m, which is equal to gm by r square multiplied by m. So it comes out to exactly the same as this one. All right. So that is the gravitational field intensity. But there's another thing which is called gravitational potential or gravitational potential energy. Potential, I will first talk about the energy and then the potential. Now, gravitational potential energy, let's say there is this one body of mass m and there is another body. When I leave it, do they get attracted towards each other? Let's say this is very massive. Then this object gets attracted towards this one, and if I leave it free, then it starts to accelerate, and after some point, let's say it has gained some velocity. But due to velocity, it must also have something called kinetic energy, right? Because kinetic energy is nothing but half mv square. If it has a velocity, it must also be having some kinetic energy, and that means that there must be some potential in this body or in this system of body to generate mechanical energy into the system. This sort of potential of the body to generate energy, mechanical energy, is called potential energy. Potential energy, which is actually equal to the work done by the system, right? And what is the work done on any body? F dot ds, right? FDS. Let's say it has moved at r distance. Then what we have over here is, what was that? Gm small m divided by r square into dr. What's the integration of this one? Since this is a constant, it will come outside, and the integration of this one is actually equal to minus g capital M small m divided by r. This is the gravitational potential energy of the system, actually. Minus g capital M small m divided by r, nothing else. This is the gravitational potential energy. So this was the gravitational potential energy, and what was the velocity that we had calculated? The velocity was this one, right, for a satellite. And what would be the potential energy? Potential energy will be equal to minus g capital M divided by the small radius r, the whole radius, or the distance between the satellite and the center of the earth. And this u will give me kinetic energy also, which is in the form of half m u square. We are talking about the satellite now. We are only talking about the satellite. What's the potential energy of the satellite and what's the kinetic energy of the satellite? Half into m into, sorry, this one, into u square. So when you square it, it becomes gm by r. So it is nothing but half into gm small m divided by r. Isn't it something in the order of this one? It means kinetic energy is nothing but uh, minus half times potential energy of the satellite, right? And when you have to calculate total energy, it will be equal to potential energy plus kinetic energy, which will be equal to this thing plus half into g capital M small m by r. This is minus 1, this is plus half, so it will lead me to minus half into g capital M small m by r. This is the total energy of the satellite. These three things you must be having in mind. It is straightforward asked sometimes. So these are the things that we need to discuss about the satellite. And there is another thing which is very small, the escape velocity, or it is also called escape speed. Escape speed. How do you find escape speed? Or first of all, what is escape speed? Escape speed is means when, if you have something called any body, if you throw it, let's say you throw it upwards, it does come back, right, due to gravitation. But let's say you throw it this fast that it goes till infinity, and if you have the body at infinity, a very high distance away from it, there will effectively be no gravitational force to pull the body back, right? Which means it is the velocity with which you must throw a body to make it go out of the gravitational pull of the earth. That is called the escape speed. And which means this should be, or if you consider the situation, we have something called initial potential energy. The final potential energy is actually zero because it is in the order of gm small m divided by r. If you have r which is very high, in this case infinity, that will become zero. And you are already taking the case which is the minimum amount of speed that you need to throw the body, which means when you throw the body from here, it is at u, but while it reaches infinity, it will eventually lose energy to zero, which means the change in potential energy should be equal to the change in kinetic energy. Change in potential energy is nothing but gm small m divided by r, because the final potential energy was 0, and the change in kinetic energy is nothing but the initial kinetic energy and minus the final kinetic energy. Final kinetic energy is also 0 because the velocity there is 0. Half m to m into v square. What was v square here? gm by r. gm by r. This gets cancelled out. Wait. I think something is missing here. Half m v square, right? So, just a second. What is the escape speed? How do you find it? Escape speed is nothing but the velocity with which it should be projected such that it leaves the potential or the potential field or the gravitational field of the earth. So the loss in potential energy will be equal to half into m u square, and that should be equal to the loss in kinetic energy, loss in potential energy, that is nothing but gm by r. When you this thing, so a small m gets cancelled out. I actually wrote the same thing on both sides. Change in kinetic energy is equal to change in potential energy. That's what we are calculating. So u square is nothing but 2g small m or capital M divided by r. So u is equal to under root 2gm by r, where r is the radius of the or the distance between the body and the center of the earth. It doesn't have to be this on the surface of earth. If it is, it will just become re. Or if it is at a certain distance from the surface of earth, r will become the radius from the center of the earth. So if that is clear, I think we can quickly move through the other parts. This is the escape velocity. When you calculate this, it is actually the same as this, right? What we calculated here. You can calculate it if you want. That will come out to be 11.2 kilometer per hour, and this is something we already discussed. This polar satellite and geostationary satellite are no longer in your syllabus. It has been deleted, so it is not relevant. But still, I will just give you a very basic thing. Let's say you have a satellite which rotates in this fashion on the this thing, the equator, above the equator, such that it rotates with the same omega. It rotates with the same omega as the omega of the earth. What that will lead to is, if you if the satellite is here and a person looks here, or a person looks above, he will see the satellite above him. But as the earth rotates, the satellite will also rotate with the same angular frequency or angular velocity, and that's why the person will see the satellite to be stationary. That is called geostationary satellite. And polar satellite is nothing but a satellite which revolves in this fashion, above the poles. It goes above the poles. So these are not important as of now. Something which was left is this part, Kepler's laws. Very important because the third part is somewhere, or the second is also very important, as some questions are asked in this part. So I'll quickly go through it. What this talks about is, yes, Kepler's laws of planetary motion. What this says is, the first law says that every planet moves around the sun in a elliptical orbit, not a circular orbit that we assumed till now. Elliptical orbit. And let's say this is the planet P, then the sun is either on this focus or that focus, either on one of the focus, it is there. the sun. Actually, in astronomy, we know that there are certain solar systems in which there are two suns inside a planetary motion. The both of the suns are at the focus of the uh, elliptical orbit. But in our solar system, there is only one sun, which is at one of the focus of the elliptical orbits of the planets. All right, that is the first law of Kepler. The second law says that the rate at which, let's say, it was here, and after certain time t, it comes here. The area which it subtends, the let's say this was t1 and this was t2. So delta t is equal to t2 minus t1, which is the time taken for the body to go from the position first position A to position B. Then the area which is subtended by the, or which area which is covered by the planetary motion, let's say this is A. If the body comes here and we again record the motion for a certain difference in time, which is the same difference in time delta t, then the area which is subtended again will be the same. It means the rate of the change of area which is subtended by the planet around the elliptical orbit is going to be constant. dA by dt is going to be 0. I'm not going to in the detail, but when you derive it out, it comes out to be that the angular sorry angular momentum angular momentum of the planet is actually conserved. This you have to remember, these two things, this one and that the angular momentum of the planet is conserved. Sometimes a few questions arrive from this part. The next is the third law of Kepler, which tells me that the time, see, third law of Kepler, in which when you what you assume from here is, let's say when you do some calculation, see, when you assume that the orbits are circular in nature, when you find the time period, it will not actually come out to be in the order of t square is directly proportional to a cube. A cube means the semi major axis. What is the semi major axis of an elliptical orbit? Let's say this is the ellipse, then this distance is called the semi major axis, from the center to one of the extreme points, the bigger one. This is called semi minor axis. Let's say this is A. Then what this says, the third law of Kepler says is that the time taken for the body to make one rotation in the circular orbit, it is going to be directly proportional to a to the power 3 by 2. The time taken by a planet to rotate for one revolution around the sun, it will actually take in the order of, or it will be proportional to the semi major axis raised to the power 3 by 2. It can also be written in the format of t square is directly proportional to a cube. Let's say there are two different systems in which the sun and the earth are the same, having the same mass. Sun and the earth having same mass, but in one case the the ellipse looks something like this, in which the semi major axis is maybe 150 million kilometers, I think you may be remembering, and there is another system in which the semi major axis is actually equal to maybe 50 million kilometers, and there's the same earth and the same sun. Then if it takes 1 year, how much time will it take? It will take actually t is equal to t dash, or t dash is equal to t into um, 50 divided by 150 to the power 1, sorry, 2, 3 by 2. All right, so this will be, t dash will be 1 year multiplied by 1 by 3 to the power 3 by 2. You can calculate this number. I think it will be smaller than 1, of course. So what it means is the time period of the planet will be directly proportional to the uh, length of semi major axis raised to the power 3 by 2. All right, I think we have covered this part of the mind map as well, this one, and I don't think any part of it left, so I think that was it. Please ignore this part, not really important as of now. It has been deleted from the uh, syllabus. So thank you for the for your attention.